Hello everyone, this is M. Saranya working as an assistant professor in the Department of AIML in MLR Institute of Technology. So today I am going to discuss about the topic of RSA and Diffie-Hellman key exchange algorithms. These are the two algorithms which we have going to define and we need to solve the problematic part also. So firstly, what is meant by RSA algorithm and example of RSA algorithm? What is Diffie-Hellman key exchange algorithm and example of key exchange algorithm? In this video, I am going to discuss about these four topics of RSA, example of RSA, Diffie-Hellman and example of Diffie-Hellman key exchange algorithm. So coming to the what is meant by RSA algorithm. Firstly, RSA stands for Ron Rivest, Adishamir and Leonard Edelman, which was published in the year of 1977. So, RSA is nothing but an asymmetric algorithm and it works on two different keys. One is public key and another one is private key. So, this RSA algorithm based upon the factorization of large number and also modulo arithmetic for encrypting and decrypting for the data. So, we are using the two keys, one is public key and another one is private key, which is also a factorization of large number and it is a modulo arithmetic for both encrypting and decrypting data. So, it consists of mainly three stages. First one is key generation, second one is encryption and third one is decryption formats. So, key generation is nothing but a creating of public keys and private keys and encryption is nothing but a those who is going to send the message to the sender, it encrypts the data by using the public key to get the ciphertext. Ciphertext is nothing but an conversion of the plain text of original one. The next one is decrypting. Decrypting is nothing but an whatever we are get to the original data to get the original data using as private key. So these are the three keys we are mainly using in the RSA algorithm. One is key generation, second one is encryption and third one is decryption process. Let us see an example of RSA algorithm. So we are going to see as a three steps: key generation process, second one is encryption process, third one is decryption process. So in this three process, we can see the one by one step process. First one is key generation. In this key generation, we need to follow some of the steps. First one is we need to consider two large prime numbers, such as P equals to 3 and Q is equals to 11. P is equals to 3 and Q is equals to 11. So, next one, we need to calculate N equals to P into Q. N equals to P into Q, P is nothing but 3 and Q is equals to 11. 3 into 11 is nothing but n, value of n equals to 33. 11 3s are 33, so value of n. The next one, we need to calculate phi of n equals to P minus 1 into Q minus 1. So, phi of n equals to, already we know the value of P, that is nothing but a 3. 3 minus 1 is nothing but a 2 into Q is nothing but a 11. 11 minus 1 is nothing but a 10. So, here the value of phi of n equals to 20. So, we got the values of P, Q, N and phi of n. In the next step, we need to choose the value of E such that 1 less than E less than phi of n and GCD of phi of n comma E should be a 1. We should be equal to 1. So I am taking here the value of E equals to 7. We need to check the process of from E equals to 1 up to E equals to 7. So I am taking the value of E equals to 7, which will be equal to the 1. So what will be happen? 1 less than, 7 less than, phi of n, already we know the value equals to 20. So pi of n value is nothing but 20, and GCD of pi of n value 20 comma E equals to 7 equals to 1. So GCD of 20 comma 7 equals to 1. While we are calculating GCD of 20 comma 7, we need to get the value of 1. So therefore E equals to 7. So already we got the value of P equals to 3, Q is equals to 11, N equals to 33, and pi of N equals to 20, and also E value we have got. The next step, we need to calculate ED mod pi of N equals to 1. So we know the value of E. E is nothing but a 7. 7 into D mod pi of N equals to 1. 7, we don't know the value of D. So mod phi of n value is 20. So equals to 1. For example, D equals to 1 to D equals to up to 6 by we are going to calculate. We need to get the value of 1 up to 1, means it should be equal to 1. For example, I am here taking the value of 3. 7 into 3 mod 20 equals to 1. It is nothing but a 21 mod 20 equals to 1. So now the value is clear with the value of 1. 21 mod 20 equals to 1 means which is nothing but a GCD mod value is nothing but, while we are going to consider by remainder. When we are getting the value of remainder, we need to consider that remainder point as mod value. So we got the D value also. In the next step, for doing encryption and decryption process, we need to know public key and private key. For doing the encryption and decryption process, we need to know public key and private key. So these both keys have to be seen. First one is public key. Public key equals to E comma N. Then private key equals to D comma N. For this knowing of values, we are going to the previous slide. P is equals to 3, Q is equals to 11, N equals to 33, pi of N equals to 20, and E equals to 7 and D equals to 3. So write down here, P equals to 3, Q equals to 11, E equals to 7, D equals to 3, pi of N value equals to 20. So all the values we have got it. Then now public key. Public key is nothing but a formula is E comma N and private key is D comma N. Encryption and decryption process. We need the value of N. So E already we know the value 7 comma N. N is also we got the value of N also, that is 33. So N value is 33. Already we have got in the previous slide, that is N equals to 33. So E comma N value 7 comma 33 and D is the value of 3 comma 33. So we got the values of public key and private key also. Now we need to find out the encryption and decryption process. As we discussed about the key generation process, second step is encryption and third step is decryption process. So already we have completed with the first process, then we need to see the second process and third process of encryption and decryption process. So next one is encryption process. encryption process. In this encryption process, C equals to ME mod N. This is the formula for encryption. The next, decryption. We can write the formula of decryption also. M equals to CD mod N. This is the formula for decryption. We know the values of all values of P equals to 3, Q equals to 11, N equals to 33, phi of N equals to 20, and E equals to 7 and D equals to 3. So we got the every values of P from to D. So I am now substituting of encryption process C. C is nothing but here we need to know the value of C. So by assuming M less than N. So already we know the value of N. N is nothing but a 33. For example, M equals to 31. We need to test the value of M equals to 31. For example, if I substitute in this formula, C equals to 31 power E. E is the value of 7. 30 power mod whole power 7 mod N equals to 33. So while substituting this 31 whole power 7 mod 33, we will get the value of 4. We get the value of 4. So this value we need to substitute here of C, because while we are substituting 31 power 7 mod 33, we need to get the value of 4. So 31 value of 125, 161, 44, 444. This is the value. We got the power of 31 whole power 37 mod 33. While we are doing with the mod value of 33, we will get the value of C. So we need to find out the decryption also. So here decryption M equals to C value 4 power D. D value is nothing but a 3 mod N. N is nothing but a 33. 4 4 16 and 16 4s 64. 64 mod 33. We will get the value of here 2. So M equals to 2. So now the keys are going to be exchanged 4 and 2. So therefore RSA algorithm has completed. RSA algorithm completed. So we got the C equals to 4 and M equals to 2. So what is the main basic theme of this? The sender encrypts the data to get the ciphertext, decrypting the ciphertext using the private key to get the original data. So we have seen the example also. The next topic is Diffie-Hellman key exchange algorithm. In this Diffie-Hellman key exchange algorithm, it is used to establish a shared secret key that can be used for secret communications while exchanging data over a public network. While we are exchanging the data over a public network, we are using the shared secrets key, and it also nothing but a exchanging between sender and receiver. Exchanging is nothing but the exchanging keys between the sender and receiver is nothing but a Diffie-Hellman key exchange algorithm. So we will consider here 4 variables of prime value P and G, such that, for example, here A is there, I am taking here alpha, primitive root of P is nothing but here I am taking is the value of Q. So alpha such be a primitive root of Q, so such that the values will be an A and B. So here I am taking the uses of Alice and Bob. So here took the private values of A and B, so that they can generate key and can exchange it publicly, not as privately. So it can be taken as publicly. So in the same process, the opposite person should also receive the key, and it should be generated as a secret key. It should not be a public and it should be an secret key, which they have the same key to encrypt the process. That is called as an Diffie-Hellman key exchange algorithm. In the next slide, we are going to see as an example of Alice and Bob. So already we have ticked the public keys of P, G. So same Bob also is going to be taken. Private key is taken as an A and the public key is taken as an B. So this is the formula for the key generation, and these are the key generated, again value of X and Y, such that the both keys should be an exchanged. Means, for example, K1 equals to K2. We need to prove this K1 equals to K2. Means the keys are exchanged successfully in the Diffie-Hellman key exchange algorithm. So the key received for the Alice is Y and the key received for the Bob is X. Then generated key should be an formula of X equals to GA mod P. So while we are substituting here, we need to take the Bob 1, again opposite of Alice 1. So algebraically we need to show that the KA is equals to KB. That is nothing but an K1 equals to K2. So let us see one example of Diffie-Hellman key exchange algorithm. First process, consider prime number of Q. Let us take an example of Q equals to 7. So we need to take alpha is a primitive root of Q. Primitive root of Q. So we need to prove that the alpha is a primitive root of Q. For example, primitive root is nothing but a, what is meant by primitive root? Let us find an example. Primitive root. What is meant by primitive root? For example, alpha power 1 mod Q, alpha power 2 mod Q, alpha power 3 mod Q, and so on, alpha power Q minus 1 mod Q. It means the values taken as 1, 2, 3, 4, 5 and so on up to Q minus 1. Whatever we are going to value of up to Q, it should be taken as a Q minus 1. That is nothing but an primitive root. So let us take an example of alpha equals to 3, Q is equals to 7. We need to find out the alpha is a primitive root of Q. So let us take an example of alpha is equals to 3 and Q is equals to 7. We need to find out here of, in this formula we need to substitute the alpha value and Q value. So alpha power 1 is nothing but an 3 power 1 mod Q. Q is nothing but a value of 7. 3 power 1 mod 7 equals to 3 mod 7 is nothing but a value is 3. 3 power 2 mod 7. 3 3 is 9. So 9 mod 7 equals to 2. 3 power 3 mod 7 equals to 3 3 is 9. 9 3 is 27. 27 mod 7 equals to value is 6. 3 power 4 mod 7 value is 4. Again 3 power 5 mod 7 equals to 5 and 3 power 6 mod 7 equals to 1. So we got the values of 1, 2, 3, 4, 5 and 6. We got the values of up to 1 to 6. Like that we need to see the alpha is a primitive root of Q. So we got the each and every value from 1 to 6. So we have proven that alpha is a primitive root of Q. It is nothing but a 3 is a primitive root of 7. Primitive root of 7. We have found out the primitive root of 7. 3 is a primitive root of 7. First we need to consider the prime number. We need to take the Q value. So such that we need to find sum of the primitive root. We have taken as alpha and Q. So primitive root is nothing but an alpha power 1 mod Q, such that we need to find up to alpha power Q minus 1 mod Q. So we have substituted by taking the values of alpha is equals to 3 and Q is equals to 7. So I have substituted in this formula. So we got the up to 1 to 6 values. Hence it is proved as an primitive root of Q. It is nothing but a 3 is a primitive root of 7. In the next step, we need to calculate XA and XB. Firstly, we need to calculate XA. XA such that that is a private key of A. So XA. So it should be a XA less than q. So we need to calculate here in the XA process YA equals to alpha power XA mod q. We need to calculate YA equals to alpha power XA mod q. So let us take some values. XA equals to 3, q value equals to 7, alpha equals to 5. So I have taken the values for example of XA equals to 3, q is equals to 7 and alpha is equals to 5. We need to find out the value of YA. So YA equals to alpha value 5 power XA 3 mod 7. 5 5 is 25, 25 5 is 125 of mod 7. We will get the value of 125 mod 7 equals to 6. So we get the value of YA. Then next, we need to calculate of the next one XB such that XB less than Q. It is the private key of B. So we need to calculate here YB. YB equals to alpha power XB mod Q. So we already know the values of alpha equals to 5, Q is equals to 7 and XB equals to, what is the value of XB? We need to find out the XB value. So XB equals to, don't know. So already we know the value of YA. Okay. So here we need to find out the value of YB equals to alpha power 4. So already we have taken here the XA equals to 3. So I am taking here the XB value equals to 4. So YB equals to alpha power XB, how much value? 4. Alpha power 4 mod Q. Here alpha value how much? 5. 5 power 4 mod Q. YB. We need to find out the value of YB. So YB equals to 625 mod 7. Q value is 7. So YB equals to, while we are substituting with the mod of 7 with the 625, we will get the value of YB equals to 2. So therefore, we got the value of XA equals to XA comma XB and YA comma YB. So we got the 4 values XA, XB, YA, YB. How much the values of XA? XA is the value of 3. XB value of 4, YA value of 6, YB value of 2. So we got the XA, XB, YA, YB 3, 4 and 6, 2. So in the last process, we need to see the K1 equals to K2 shared the keys successfully or not. We need to check it. Shared the keys successfully. So we need to find out the K1 equals to K2 shared the keys successfully or not. So let us assume K1 equals to 1%, K2 equals to another person. So we need to find out the K1 and K2. K1 equals to YB power XA mod Q and K2 equals to YA XB mod Q. K1 equals to YB power XA mod Q and K2 equals to YA power XB mod Q. So K1 equals to, already we got the values of XA, XB, YA by B. What is the values of XA, XB? 3, 4 and 6, 2. So now substitute in these values by using this formula. So YB value is 2, XA value is 3, mod of Q is equals to 7. 2 2's 4, 4 2's 8, 8 mod 7. While we are substituting 8 mod 7, we will get the value of K1 equals to 1. 8 mod 7 value is 1. So K1 equals to 1. Then K2, YA value 6, XB value 4, mod Q value is 7. So 6 power 4, 6, 6, 36, 36, 6, total of 1296, mod of 7 value. So by substituting 1296 with the mod 7, 7 value with 1296, we will get the value of 1. K1 and K2 we got the value of 1. So that the K1 equals to 1 and the K2 is also 1. Therefore, K1 is equals to K2 means shared the keys successfully. So it shared the keys successfully. It means establishing a shared key by using and exchanging data over a public network. Already we have discussed, by using these generation keys, we need to exchange the keys by K1 and K2. That's why we have proved here K1 equals to K2 such that we need to be shown as an K1 equals to K2. The definition of Diffie-Hellman key exchange algorithm is nothing but a, while we are sharing the keys by sender and the receiver, between the sender and receiver, we need to exchange the keys successfully or not. For example, K1 is getting a different value and K2 is getting the different value based between the sender and the receiver. It will be a wrong, because K1 while sending an information to the receiver also should get the same information. While the receiver sending the information again to the sender also should get the same information while sent by the receiver. That's why we need to prove here the K1 equals to K2. Hence, it should be proved shared the keys successfully. So that is the process of Diffie-Hellman key exchange algorithm. So we have discussed today in the RSA algorithm and its example, and Diffie-Hellman and its example. In the next section, we need to go in to discuss about the OSI security architecture, active passive attacks and steganography process. Thank you.